This is Kyle Schroeder, and I'm partners with Joey Osbon, and we did oxyacetylene torch testing of materials. The objective of our experiment was to calculate and analyze the heat transfer coefficient during heating and the heat transfer rate during cooling of a composite material. During heating, we used a heat flux Q double prime. During cooling, we used the equation that our total heat transfer rate is equal to our heat transfer due to convection plus our heat transfer rate due to radiation. In order to obtain the heat transfer rate due to convection, we used Grashof numbers, Prandtl numbers, and Nusselt correlations. You see on the left there are three types of flames an acetylene torch can produce, the first being a neutral flame, secondly an oxidizing flame, and lastly a carburizing or a reducing flame. Note a neutral flame has a small inner cone and a larger outer envelope, while an oxidizing flame has a medium-sized inner cone and a small and narrow outer envelope. A carburizing flame is much like an oxidizing flame, but it has an acetylene feather as well. You see on the right there are graphs of the heat flux plotted against distance for each of these three flames, with an oxidizing flame having the greatest heat transfer rate or heat flux, where a neutral flame and a reducing flame have smaller values for heat flux. In order to verify the heat flux, we used a thermopile. Thermopiles work much like thermocouples. They use dissimilar metals to produce a voltage. So we ignited our acetylene torch, placed a fire brick in front of it, brought a thermopile into the flame for a short period of time at around 40 millimeters. We recorded the voltage from the thermopile, and from this data we could easily calculate the heat flux. Our testing continued as we placed our advanced ceramic in the same location as the fire brick. The acetylene torch was ignited and placed into position. During heating and cooling, the surface temperatures were measured, and we stopped measurements once the sample reached 1,000 degrees Celsius. You see on the left is a picture of our high accuracy 2-color infrared pyrometer, and on the right is a picture of our advanced ceramic glowing white hot. The picture on the right is through a welding shade because the ceramic got so bright you couldn't view it with a normal lens. Here's a plot of our experimental heat flux values we obtained from our thermopile, plotted against the published values we showed earlier. Note that our experimental values are pretty close to our published values, and this is good. This is what we were hoping. We did this by regulating and monitoring the gas flows and pressures as outlined in the published paper. Here's a plot on the left of our heat transfer coefficient during heating. You'll note at the beginning it's very high, and as we reach the end of the test it starts to level off. This is to be expected since we're starting to reach a steady state condition. On the right is the total heat transfer rate plotted against the heat transfer rate due to radiation only. And we were anticipating that these would be very close because at these very high temperatures, radiation is a dominant form of heat transfer. Again, we found our heat transfer rate due to convection. That's the only difference between these two plots by using Grashof numbers, Prandtl numbers, and Nusselt correlations. This experiment verified many of the assumptions that we made. The first, that the published values of heat flux for an acetylene torch were accurate, and we verified that with pretty good confidence. Secondly, there's a lot of things that can be found from this. You'll note in the second equation here stating that heat transfer rate is equal to a heat transfer coefficient times the surface area and the change in temperature. Having used this plot from the published values, you could find Q and the area will cancel. That leaves H to be found. H can be found using Nusselt correlations. However, since you need a Reynolds number in Nusselt correlations, you would have to either measure the velocity or the free stream velocity of the acetylene, or you would have to find it using mass balance. This is a little complicated because that would require compressible flow analysis, which is a little beyond us. But in a graduate level course, you would be able to solve for that velocity and then find h through Nusselt correlations and then be able to solve for various surface temperatures at different distances.